Hello. Very glad to see you. So let's start our class. I would like to ask you whether you know, is Michael going to be here today? Because I asked him to prepare a board for us. But unfortunately, I cannot see him today. So let's use some new kind of board. I'll share you. Wait a minute, please. So I've just sent a link to a board for you, and I'll share my screen with you now. So here you are. Okay.
Sorry, it seems to be private. Request needed.
Oh, wait a minute, please. I'll change the settings. So now you all can see and even edit.
Yes.
So I suppose. Oh, here's Michael. Michael, I just sent a Jamboard to everyone, but maybe you have more convenient board.
Actually, I can do a board just in a minute. Sorry. Give me a minute.
A minute, okay, because I haven't prepared a board for us, a mirror board for us. I hope that you'll help me. So, okay, let's start discussing our problems for today's class. And the first one, we don't need a board for the first problem, actually. So let's remember which numbers can be the orders of any finite field. From the lecture, maybe you'll remember. Right? Guys, who can tell us which numbers can be orders of finite fields from the lecture? Do you know, for example, a field of 10 elements, or maybe 15 elements, or 5 elements? And what is the difference between a field of, say, 10 and 5 elements? How can we build them if we ever had? So I would like you to remember something from the lectures, something
And,
about fields.
We can have like field. It is almost same as we had like some group. It have to be ring, yeah.
It have to be ring, yeah. But every non-zero element should be invertible. Mm-hmm. First of all, do you know a field of 2 or 5 elements?
Yes.
Mm-hmm. What about 4, for example, elements? Are there any fields of 4 elements? Okay, first of all, if P is a prime number, what can we say about a possibility of a field of P elements? Is this true that for every prime P, there exists a field of this number of elements? Is it right? Guys, is it right that for every prime P, the ring of remainders is a field?
It is true because like as these numbers are co-prime with our cardinality of our field, then we can find an inverse of each number.
You're absolutely right. And what about their powers of prime numbers? For example, p to the nth power, where p is prime and n is some natural number.
No, because like because some numbers will be won't be co-prime with with cardinality of our field.
So the ring that p to the nth power won't be a field. But are there any other fields with this number of elements? So is it true that we can build a field of cardinality p to the nth power for every prime p?
Sorry for interrupting. I think I prepared board, so you can turn it in.
Okay, thank you. I'm trying to send the link to my tablet now, actually. So this is a problem because my so in a minute I can write on this board. Okay. So the question is, maybe you can remember how to construct a field consisting of p to the nth power elements.
And actually, it will be all prime numbers in this set.
That's true. So all prime numbers will be in the answer. And what about the powers of prime numbers? For example, 4.
Can we check it?
How can we check it? We can construct such a field and try to construct such a field and see can we do this or not. Okay, so let's skip this problem for now and try to solve some other. For example, number 3. Okay, let's see to the problem number 3. Here, they ask us to produce explicitly the field consisting of 4 elements, yeah, and compute the product of 2 arbitrary elements. Okay, the recipe of constructing such kind of fields. First of all, you see here that the number of elements is 2 squared, yeah? Mm-hmm. So what is the characteristic of this field? The characteristic should be prime, and this is a number of ones. We need to construct 0, the minimal natural number of ones, such that 1 plus 1 plus etc. plus 1 equals 0. Okay? So this minimal natural number is a characteristic of this field. And from the lecture, maybe you remember that for every finite field, the characteristic should be prime. Okay? Mm-hmm. Because if it's not prime, let's say that the characteristic equals m times n. It means that m ones multiplied by n. So we take these numbers in brackets, n times this is a multiplication. So here m, here n, we multiply them, and we get 0.
Galina,
because
sorry for interrupting. Can you please share board over like in Zoom, because I see that only 5 people in like on the board and a lot of people here, so maybe they do not know how to access it.
This will be better. Okay, so we supposed that the characteristic of a field is not prime number. So let's factorize this number into 2 factors, m and n, and take this number of ones and add all these ones. It means that we can multiply sum of m ones and sum of n ones. And this is a non-zero number in our field because the characteristic is greater than m. And this is a non-zero number, yeah? And the product of 2 non-zero numbers in our field equals 0. This is a contradiction. There are no 0 divisors in our field. So the characteristic cannot be factorized into non-trivial factors. So the characteristic is prime always. If you remember, something like that was in your lectures. And Dima Trushin proved that this is true. Okay, so now we know that the characteristic is prime, and the number of elements can be represented in the form characteristic to some power. So the characteristic equals 2, because this is our prime number. So how can we now construct explicitly our field? Let's take a field of characteristic 2, but such a field that we know. I mean the field of reminders, modulo 2. And let's take a ring of polynomials of of x, yeah, over this field. And then factorize this ring of polynomials by an ideal which is generated by some polynomial which is irreducible. Do you agree that this polynomial is irreducible? It's irreducible if and only if it has no roots. So 0 and 1 are no roots of this polynomial, okay? Mm-hmm. And then what do we get after this kind of factorization? First of all, we get a field. This is also a fact from your lectures. If we factorize by ideal generated by some irreducible polynomial, we get a field. So this is a field. What is the characteristic of this field? This is the same as the characteristic of our base field, Z2, right? Because since 1 plus 1 equaled 0 in Z2, here in this vector ring, 1 plus 1 is still 0. So the characteristic equals 2. And how many elements are there? Let's write down the list of all the elements in this field. First of all, this is 0 and 1. They're the elements. Then some polynomials, x. Then x plus 1. What else? Actually nothing, because let's consider some polynomial of second degree. Suppose there is some of them. Or even the degree will be more than 0. What can we do? We can write down that it equals to x squared plus x plus 1 by some q plus some remainder r, where the remainder is a polynomial and the degree of this polynomial is less than 2. So this is one of these 4 polynomials, 0, 1, x, x plus 1. And we know that in factor ring, since we factorized by ideal generated by this polynomial, in the factor ring, our polynomial of second degree and our remainder r belongs to the same coset. So in factor ring, this is actually the same element, you see? So every element can be represented as a polynomial of degree which is less than 2. So that's all are our elements. And there are no other elements. Is it clear that our field is already built? We constructed our field as a vector ring of some polynomial ring over some ideal generated by a polynomial. And we wrote this polynomial explicitly. And we've showed that there are 4 elements in this field. So, do you have questions concerning this procedure of constructing a field? No questions. Okay. How can we find the number of elements in such kind of vector ring? How can we find it? We need not write down all of them, because we know that all the elements could be represented as polynomials of degree which is less than the degree of this polynomial. So we have to put zeros or ones or any other elements which could be in our field here as a coefficients of our polynomials. So we have all the polynomials of degree which is less than degree of this polynomial, and we can put all combinations of coefficients. There are n-1 coefficients. Since the degree of this polynomial is n, there are n-1 coefficients here, and we can put how many of them? In our case, 2. Here and here. So the number of elements equals 2 by 2 in our case. In more general case, it will be the number of elements in our base field, say, let it be ZP. So we put P, and there are n places. So the number of elements equals n, because there are n coefficients in a polynomial of degree n-1. Okay, so this is a general recipe for producing a field of p to the nth power elements. Okay, so what should we do now? We should compute the product of two arbitrary elements of a field. Let's do this. This is the next problem. Okay, so let's do it here. What is the product of 0 and every other element? We know this is 0, 1, and every other element, this is this element. And we are interested only in these three products. Thank you. We are interested in these products: x squared, x times x plus 1, and x plus 1 squared. Yeah. We need to represent these polynomials as a polynomials of degree which is less than 2. So this equals minus x plus 1, because it's reminder minus x minus 1, but actually it is the same that x plus 1, because in the 2 minus 1 equals 1. Okay, then here x times x plus 1. This is x squared plus x. What is the remainder of this polynomial? Modulo x squared plus x plus 1. The remainder equals 1. And here x plus 1 squared equal to x squared plus x, which is 0, plus 1. X plus 1 equals 1 modulo x squared plus x plus 1. So that's all for our field. Questions? Please ask me if something isn't clear. Is this clear? Okay, let's look at the first problem one more time. and write down the answer here in the first problem. So we already know that all the prime numbers are in the answer. So 2, 3, 5, and 7. There are fields with such a number of elements. But what about?
And there are three like numbers which are powers of prime numbers. It is 4, 8, and 9.
Mm-hmm. You're right. You're right. There are 3 more fields consisting of 4, 8, and 9 elements. And now we know how to construct them. In this case, we've already done it. In this case, in the second case, we take Z2 and then the ring of polynomials, and then we have to factorize by ideal generated by some irreducible polynomial of degree 3. You see? And here we have to factorize a ring of polynomials
of degree 2
over Z3 by an ideal generated of irreducible polynomial of the second degree. And that will be the explicit construction of the field. Okay? So let's go on. The second problem. The second problem is about a field of characteristic P, non-zero characteristic. We now know that P should be prime. We have to show that the map by the rule x goes to x to the p power is an injective homomorphism. First of all, let's remember, what shall we prove? We have to prove that x plus y to the power p equals x to the power p plus y to the power p. Yeah, and that xy to the power p equals x to the power p, y to the power p. What is trivial? This equality is trivial because the multiplication is commutative in every field. So we multiply the powers, and that's the same that multiply the, first of all, multiply all x's and then multiply all y's. So, well, what about the sum? Let's see. How can we represent this power? Actually, this is a sum of terms of the following kind. First of all,
binomial coefficients.
Binomial coefficients, yeah, you're absolutely right, thank you. Here, and x to the power k, y to the power p minus k. Let's see to the first and the last terms of this sum. The first term is x to the power p. The last term is y to the power p. And what about other numbers? Let's look at one of them. This is p factorial over k factorial over p minus k factorial. Remember that the characteristic of our field equals p. So we know that p equals 0 in our field. And here, what can we see? We see that this is an integer number. We know that binomial coefficients are integers. And we know that this number is divisible by p, right?
Mm-hmm.
This is divisible by p because the factor p is in the numerator, and here in the denominator there are no such a number. Okay, so this is
Oh no, I don't have a question.
Okay, p is prime. I suppose the answer was p is prime. So we see that this number is 0 in our field. So there are no coefficients, no non-zero terms in this sum, except x to the power p and y to the power p. And what if we prove? We proved that the sum of the sum is mapped to the sum of phi's of our x and y. So phi is a homomorphism. Here we wanted to prove that phi is an injective homomorphism, and now we know that it is a homomorphism. So let's check that it's injective. So I write down here that phi is a homomorphism. So suppose that phi is not injective. Let's suppose that there exist x and y such that x to the power p equals y to the power p. So the images.
Sorry for interrupting. I have a question. Why can't we prove that phi is homomorphism just by inverting phi? We know that if phi inverse is homomorphisms, then phi is isomorphism. Why can't we do so?
Okay, and how can we construct the inverse elements for every element in F?
Inverse.
So we need to extract roots. We need to extract roots. We take some arbitrary element, say, let it be Z, and we need to find such an element, say, Z hat, such that this element to the power p equals our element Z. How can we find it? So to build an inverse homomorphism is this type of procedure. And explicitly, it's difficult to do it explicitly. We don't know for sure how to do it explicitly. So this is the problem.
Oh, okay, got it.
And we'll solve this problem, but not in the direct way. Okay, look. First of all, this homomorphism is injective. Why? It's injective. Suppose that there are two elements with the same image. Let's consider x minus y to the power p. We've almost done it before. This is x to the power p minus y to the power p. Phi minus here. If p is an odd number, yeah, we have minus here. And if p equals 2, minus or plus here, it doesn't matter, because minus 1 equals 1. So we can put minus here. And what do we know? We know that
And shouldn't it be n minus 1 to the power p? Because, for example, if we have, if our p is even number, then like this expansion, I mean the expansion which we used with binomial coefficient, it won't have like p to the y to the, it won't be like minus 1 to the power p.
Why? Why? It will be minus 1 to the power p multiplied by y to the power p. So there are p plus 1 terms in our product, in our sum. Yeah, here p plus 1 terms, and the first one with plus, the next one with minus 1. So the number of them is even. The first with plus, the last with minus. When p is odd number.
Yeah, but it does.
Okay.
It works only if p is odd number. And what if p is?
Yes. Yeah. And suppose p equals 2. Here we have the equality. And it doesn't matter to put plus or minus here, because minus 1 equals 1 in every field of characteristic 2.
Oh, okay, got it. Yeah.
So here we see that this is 0, because we've supposed that x to the power p and y to the power p are equal. So this is 0. And what do we know? We know that we took some number x minus y and multiply it by itself p times, and then we got 0. In every field, it means that x minus y is 0 itself, because there are no 0 divisors. Yeah. So x minus y is 0 and x equals y. So we proved that since the images of two numbers are the same, these two numbers are the same. So our homomorphism is injective. Any questions?
No.
No questions. Okay. So what else should we prove? If f is finite, we have to prove that phi is an isomorphism. So we've already checked that it's an injective homomorphism. We need to prove that phi is surjective. Let's see. Why phi is surjective. So here we have f. The map is phi. And here we have f. Since we know that there is a finite number of elements in f, and the homomorphism is injective, what can we write down? We can write down that the number of elements in the image equals the number of elements in f. I mean in this f, the first f. They're the same f's, but the first f. Okay, suppose our homomorphism is not surjective. It means that the number of elements in the image is less, strictly less, than the number of elements in all the set f. Here is the second f. And this is a contradiction, because the number of elements in f is less than the number of elements in f. So, since the number of elements is finite, here and here the number of elements is the same. So our homomorphism is surjective. So we now see that it's both surjective and injective, and it's an isomorphism. Okay? Okay. Do you have any questions? No questions. Note that we cannot use the same kind of explanation in infinite set, because we cannot write down the number of elements, which is a natural number, is less here than here, and this is a contradiction. Only in finite case the fact is true. Okay, then let's solve some other problem. The third one. Let's solve. So the problem number 4, or maybe, okay, let's solve the problem number 4. So here we'll construct a field of 8 elements. First of all, we have to check that some polynomials are reducible. Maybe from the previous practical class, from the previous of our classes, you remember that a polynomial of degree 3 is reducible if and only if it has no roots in our field. Okay, so we have to check, are there any roots in our field? Let's see. First of all, x squared plus x cubed plus x squared plus 1. Substitute 0. It's 1. And substitute 1. So it equals to 1. So the first polynomial doesn't have roots in our field Z2. The next one.
Can I try the next one, please? It seems to be pretty easy.
Okay, so please.
It is x cubed plus x plus 1. We substitute x with 0, and it is equal to 1. And we substitute x to 1. It is also equals to 1. So it is irreducible.
It's reducible, right? Thank you. So we've done the first part of our task. What can we say now? We can take these irreducible polynomials, each of them, generate an ideal by each of these polynomials, and factorize a polynomial ring over these ideals. And we get a field. In each case, we get a field consisting of 8 elements. So let me write down that these 2 factor rings are fields. So this is a field. It consists of 8 elements because the characteristic is 2 and the degree of our polynomial here is 3. So this is a field of 8 elements. And the second field also consists of 8 elements. Then we need to show that the map here in this problem is not a homomorphism. Let's see. We construct a map from the first factor ring, which is a field of 8 elements, to the second one. I'll show the screen in a minute because I need to write the polynomials. So we take every element of the first field which has form a plus bx plus cx squared and map it into a plus by plus cy squared. Why isn't it a homomorphism? Let's see. First of all, suppose this is a homomorphism. What do we know about the image of x? X goes to y, x squared goes to y squared, right?
Mm-hmm.
And let's look at some other elements. For example, maybe x plus 1 will be appropriate. X plus 1. X plus 1. X plus 1 cubed. Okay. First of all, x plus 1 cubed is x cubed plus 3x squared, which is 1x squared, plus 3x, which is 1x in our field, plus 1. And what do we know about this polynomial? It is equal to its remainder modulo x squared plus x cubed plus x squared plus 1. So this is x, right?
Mm-hmm.
X. The next one. The image of this polynomial, on the other hand, is y plus 1 cubed. Because the image of x is y, the image of 1 is 1, and the cube goes into cube. But the cube is equal to almost the same.
Y squared? It will be just 1y squared?
Mm-hmm. In our field, it is y squared. So we see now that the image of x is equal to y, because this is a definition of our homomorphism. Say it is a homomorphism. And then we've just obtained that the image of x is y squared. So y should be equal to y squared in our second field. But it's not true, because the reminders modulo what? Modulo this polynomial of y and y squared are not the same. The reminders are different. The reminders are themselves, y and y squared. So y should be equal to y squared, but it's not true in our ring, in our field. I'm sorry. So this is a contradiction. Since we've supposed that our map is a homomorphism, we've obtained a contradiction. So the map defined as here is not a homomorphism. You see?
Mm-hmm.
So any questions? No questions, everything is clear. Okay, let's go on. Let's go on and check that 1 plus y is a solution of some equation in our second field. Okay, I'll write down all that we have to check. So
in this case,
the equation is...
I have a question. In this case, we should substitute 1 plus 1 instead of that?
Yeah.
Okay, and then check is it solution?
Would you like to do this? Would you like to do this?
Yeah, I can try.
Okay, do please.
Okay, we have z squared plus is it z squared? Z cubed plus z squared plus 1 equals 0. That cubed plus z squared plus 1 equals 0. So now we need to substitute z equals y plus 1. Yeah, it is 0, sorry. Okay, and it will be y, we know y cubed. Oh no, we don't know actually y cubed. Okay, it will be y plus 1 cubed plus y plus 1 squared plus 1 equals 0. So now we can check separately what this polynomial in our field y plus 1 cubed y plus 1 cubed is y cubed plus 3 and 3 equals 0, so we can okay,
3 equals 1 because our base field is Z2.
Okay, plus 3 3y squared plus 3y plus 1, and and remainder is sorry, I forget what is our ring. Okay, and remainder is y squared. The second y squared y plus 1 squared, it is equal y squared plus 2y, it is 0, and okay, plus 2y plus 1, and it is equal y squared plus 1. So in result we have the following. Sorry, I need one more page. Okay, in the result we have it is y squared plus y squared plus 1 and plus 1 equals 0, and this is actually 2y squared and it is equal 0, and this is 2, which equals 0 in our ring, so it is 0. So y plus 1 is root of initial. It is root of is solution for initial equation.
Yeah, you're right. Thank you. Thank you for your computations and the explanation. Okay. Questions concerning this solution? No questions. Let's see. Let's see on the next part. So we have to find a solution of the equation in our ring in the form y to the power of d. And then using the solution from the previous two parts, we have to build an isomorphism, because we haven't succeeded in constructing an isomorphism yet. So let's do this. How many solutions can this equation have in our field?
Infinitely.
Now we know that.
It is infinitely many because like our field is like in a base 2. only with base 2 coefficients. And how to find them? And what does it mean, y to the power d? What does it mean? I don't actually get it.
Okay, you see that we can consider all the elements y, strictly speaking 1, which is y to the power 0, then y squared, y cubed, and y to some more powers. And we can represent all these powers as an elements, as the reminders, modulo y cubed plus y plus 1. Okay, so we can represent every element as a polynomial, but in some different ways. As an element of this form, y to some power as a monom, and we can represent it also as a reminder, modulo this polynomial, and every element has some forms. So maybe even our root, which we've already found, 1 plus y, can be represented in the form y to some power d. Okay, and let's discuss more things about these powers. First of all, this will be connected with the part G. So imagine that we took all the invertible elements of our field. What are the invertible elements of our field? They are all the non-zero elements, correct? So look at the item G, please. Here, you see the group of all invertible elements of our field, F8 start. We've considered it in one of our previous classes. So this is a group, multiplicative group of all the invertible elements. And we know that it consists of 7 elements. But what do we know about a group of 7 elements? Let's imagine it as a group that's 7. We know that as an additive group, it can be generated by every element, except, of course, neutral element. So it can be generated by 1 additively, by 2, by 3, and by all the other elements in this group. Yes? So, strictly speaking, the multiplicative group of our field can be generated by the powers of every non-zero element.
I have a question.
Every non-zero elements except of course 1, because 1 can generate any other element except itself.
I have a question, because is these groups really isomorphic? Because Z7 has 6 elements, while
Z7 has 7 elements.
Oh yes, sorry, 7 elements, and F asterisk 8 has only 4 elements, like except
why 4? Now this field consisting of 8 elements. It's not
this field. It is
a ring.
It is not.
It's not this ring. Okay, yeah. It's a field, and every non-zero element is invertible. The multiplication here is much more complicated than multiplication here. Now we've just seen that the multiplication is a multiplication of polynomials, and we have to multiplicate polynomials and then find the remainders. So this is a multiplication. It's a bit more complicated than here. So
and then I have next question. Our like our field 8, field from 8 has actually 8 elements, but that 7 has Z7 has only 7. So how can they be isomorphic if in our field we have this 0 element, this nil element, which cannot behave same as any element in Z7.
Okay, I see. This object is a multiplicative group of all invertible elements of our field. So this group consists not of all elements of our field, but of all non-zero elements. So we exclude 0 from our field and take all the rest elements as a multiplicative group. We forget about the addition. We forget about the neutral element, additive neutral element here. We remember only about the multiplication, and we take only those elements which could be invertible by multiplication. So the sets here and the set here are not the same. This set doesn't contain additive 0. You see? So there are 7 elements here, and we consider them as a multiplicative, as a set of multiplicative elements. And it turns out to be a group.
Yes, I think I got it.
Okay, nice. And here we see that this is a fact. Maybe during the lectures, you've proven this fact, but I'm not sure. You can tell me if you remember this fact from lectures, whether it was on the lectures or not. So this group is isomorphic to Z7. And how to find all the generators? We can find all the generators here, and we know all the generators. And then map these generators here, and so we know all the generators. And what generators are there? Every element of Z7 except 0 is its generator. So we know already this fact, right? Because 7 is a prime number. And this additive group can be generated by every non-zero element. Is it clear, guys?
Yes.
Okay. And now, what do we know about the images? We need not know anything complicated about the images. We only know that this 0 goes to 1 here, because here the neutral element is 1, and here the neutral element is 0. So the image, if we construct an isomorphism from Z7 to this group of multiplicative group of a field, 0 goes to 1 as the neutral element. And every other element, which is not 1 here, can be generator here, and it should be a generator here. So the generators are all the elements except 1. Is this explanation clear for you now?
Yes.
Okay, so let's look at the item D. Since we know that this multiplicative group can be generated by every element except 1, we can derive that the powers of Y are all the elements of our field, except of course 0, right? Because every element, take for example Y, generates the multiplicative group of our field. So the powers are all the elements of our field. So we can represent every element in our field as Y to some power D. And we still have to find all the solutions of this equation. And how many solutions can this equation possibly have? Tell me, please, how many solutions?
Like as much as there are generators in our group.
Why? Why? What do we know about polynomial equations over some arbitrary field? For example, over complex numbers. Do you know, for example, that every equation of polynomial equation of power n has n complex numbers, complex roots?
Complex roots, yeah, we know it.
Mm-hmm. And in the arbitrary field, they might be less than n roots, where n is a degree, but there couldn't be more than degree roots, right? Because every polynomial can be represented in a form. Let me write it down. In a form an, where this number is a coefficient of x to the nth power, and then x minus x1, etc., x minus xn, where these elements xi's are roots. If there are roots. So they couldn't be more than the degree roots, because this polynomial is a polynomial of degree n, since an is not 0. So we cannot represent a polynomial of degree n as a product of n plus 1 linear polynomials, right? So the number of roots is less than or equal to the degree. And we already found one root of this polynomial. Let's find all of them.
There are at max 2 more, yeah? Okay.
So let's check, for example, y squared plus y, and I'll show their computations with one of their powers. For example, let's take y to the power d, where d is 4. What shall we do first? We can substitute this element to our equation, or we can find the remainder and then substitute the remainder into our equation. Okay, so let's see. I'll find the remainder. It is y cubed plus y plus 1 by y plus, what else, y squared plus y. So you see the remainder is y squared plus y. We are still over the 2, and it's easy to add ones to each other. Okay, so the remainder is y squared plus y, and this is y to the 4th power. Let's substitute this element into our equation.
I have a question. But actually, this is something like very similar, because we can take y out of take y out of brackets, and then we will have the same equation as previous time, but multiplied by y.
Not
So
exactly the
therefore,
same. Let's
yeah, and then it will be exactly the same, cubed. Sorry, it is cubed.
Cubed. You're right.
Okay. And it is actually our root, because this will be 0. This also will be 0, or not.
I didn't get it. What exactly will be 0?
They won't be 0. They will be just the same coefficients. It will be something like y squared times y cubed plus y squared plus times y squared.
So let's substitute y squared here, as previously, and y squared plus 1 here. Okay, and then look, you see, very nice of you, thank you. So this is y to the 5th power plus y to the 4th power plus y squared plus 1. Yep.
Yes.
And what was our equation? X cubed plus x squared plus 1. So it is almost, we need, that's y cubed plus y squared plus 1 and plus 1 here. Yeah?
Yeah. And the remainder is just 1.
But that's not the remainder of, this is our equation, but that's not our polynomial for factorization. Yeah? So here the remainder is y squared. Yeah? Because y was not a solution. Y plus 1 was a solution. And we cannot say that this is 0 because y wasn't a solution. So we don't know it. And here, this element is y, right?
No, I don't get why.
Because if I add y here, I get y cubed plus y plus 1, which is 0, yeah? And I have to add y, and so let me write down it explicitly. So what is y cubed plus y squared plus 1? This is y cubed plus y plus 1 plus, once more, y plus y squared, right? So this is 0, and this is y plus y squared. So here, y squared multiplied by y plus y squared.
Oh, sorry. I thought that we have like our equation is y cubed plus y squared, and it is just y cubed plus just y, not squared. Now I got why it is equal to just y.
no, our equation with square, but polynomial for factorization with y, with just y, not with square.
Да-да-да,
Okay?
я понял. Я просто думал изначально, что мы, ну, как бы мы ищем остаток, с таким же уравнением, только где y в квадрате.
Остаток с изначальным полиномом.
Да-да-да, я понял.
So here, let's divide. So let's divide explicitly by y squared plus y plus 1. So we could do it earlier. Here is y. So y to the first power plus y squared plus y. Yeah. And here y cubed plus y squared plus 1 plus squared plus 1. And here plus 1 and y cubed, y and 1. So the remainder is y squared and plus 1, and it's not 0. There is a mistake here. So let's discuss what computations should we do. I suppose I've made a mistake.
But no,
but I'm not sure where.
Now you have to replace this this y squared like this. You see like this with y squared, and it will be y to the fourth power plus 1.
Plus
y
1.
To the fourth power plus 1 equals 0. Okay, plus 1, and we're looking what it equals for. Equals 2. So we have wait. Just somewhere here we already found that y to the fourth power equals to something. Yeah. It is y squared plus y.
Y squared plus y and plus 1, it's 0. Oh.
Yeah.
Thank you.
Y squared plus y plus 1.
It's still not 0.
It is still not 0.
It is still not 0. So, okay, there is a mistake. There is definitely a mistake. Okay, so let's discuss the ideas and how to solve this task. We take, okay, so here we take y to the power d, and we list all of them. By all of them, I mean 7 of them, because they are all the non-zero elements. So we take 1, y squared, y cubed, etc. And we can substitute all these elements into this equation. Then we make all the computation, we find the remainders, and the result should be the following. The remainder of all this construction, where z equals y to the power d, the remainder modulo this polynomial here is equal to 0. Since it is true, our polynomial y to the power d is a root of our equation. So I write down that our first root is y squared. Yeah, it's easy to see that y cubed is equal to y plus 1, right? So we already found one root in this form. And then we have to check some other powers of y and find whether there are other solutions. If I'm not mistaken, you'll get these ones, y to the 5th power and y to the 4th power. Okay, so we are now out of time now. Let it be your a part of your homework, but you, of course, need not write it down and send to your assistant, but it will be very helpful to check whether it is true. And we can discuss it on our Q&A on Monday. So I was waiting for you on Monday on about 15 minutes, but no one came to the Q&A. Yeah, so it's up to you. You can attend it or not. It's up to you. Okay. So we've discussed ideas of the item D, and you can do it on your own at home. And if you have some questions, we'll discuss them. Okay. Do you have now any questions concerning our today's topic?
No questions. No, actually, the idea of this solution is kind of clear, but it's like no other questions. The idea is clear. Yeah.
The idea is clear. Okay. Okay. Nice. So, some else opinions? No else opinions. Okay, so that's the end of our class. Thank you. If you have questions, as usually, feel free to text me. Visit our Q&A on Monday, and good luck with your homework. Have a good time. So, good luck and goodbye.
Thank you. Bye-bye.
Thank you for attending this class.